one slide actually on the background. So Malta is a small island where our only freshwater resource is groundwater. And therefore groundwater is an important element of our water supply and is an important element for ensuring water supply security. In fact, even today it represents around 60% of our freshwater sources. But our groundwater systems are vulnerable to surface pollution because our aquifer matrix is a fractured environment, so there's a lot of infiltration from the surface, but also being an island, our fresh water is in direct vertical and lateral contact with seawater, so we're prone to seawater intrusion. We've been using isotopes over a number of years. Our first use of isotopes goes over 25 years ago. And I will shortly describe 5 case studies. Firstly, which is where we started, is the residence time of our groundwater, how it can be determined from stable isotopes, tracing nitrate contamination, what we're doing now, characterizing seawater intrusion, and then 2 applications on a saturated zone and desalinated water. So first of all, if we look at residence time, so why is it important to know the age of your groundwater? Because basically residence time is an indicator of the resilience of the groundwater systems to quantitative stress. If the residence time is long, so over decades, that would indicate a high storage to recharge ratio, and therefore the capacity of the groundwater body to sustain short-term over abstraction. So even if you stress your groundwater body by taking up more water, it would still maintain its structure. And this is important because we're looking at climate change, we're looking at an increased prevalence of droughts and the length of droughts by climate change, and therefore this quantitative resilience is important. It's you use isotopes here, so for young groundwater, there's tritium and sometimes coupled with chlorofluorocarbons and sulfur hexafluoride. And we've used this and we've determined through the use of isotopes the residence time of our groundwater body to be of the order of 40 years, which means that it is a resilient system to episodes of prolonged drought and therefore very important in our context, and therefore this increases the need to protect our groundwater better because it can and it is important to keep it as an important source for sustaining supply security for the future. On the right side of this slide, you can see some models which are developed, piston flow models were developed with SF6 and CFCs and corroborated with tritium that actually allow the identification of residence time. The second case study is a tracing of nitrate contamination, where nitrate is definitely an important contaminant in groundwater worldwide, not just in Malta. And addressing nitrate contamination requires mitigation measures on the main, let's say, supply sources, on the main contaminant sources. But even here, determining the source of contamination when you have different users and different applications of nitrate can be important because it can lead to stakeholder conflict. So why are you accusing me when there are other users? For example, agriculture, which use nitrate as fertilizers, but we've also got nitrate in urban sewer systems which leak. And therefore, why are we accusing agriculture when some of agriculture can tell you why it's me, why it's always me? And isotopes can lead to the identification of the main activities contributing to nitrate contamination of groundwater, and therefore contribute to the development of informed policies and management plans and directing, let's say, measures to the main types or typologies of nitrate application in the surface. We've applied this technique with the support of the British Geological Survey. Basically, you determine a footprint of the different sources or the fingerprint of the different sources of nitrate through oxygen 18 and nitrogen 15, and then you can overplot the same ratios, same fingerprint for nitrate from groundwater. And in our case, most of the nitrate which we managed to fingerprint from our groundwater sources was attributed not to sewage, not to artificial fertilizers, but mainly to nutrients which were present in the soil, to soil nitrogen, and therefore over fertilization. And this opens up an argument of helping agriculture to reduce the input of fertilizers because it is even a cost for agriculture, and therefore this has helped us to explain well the situation and go to directed policies, not just to reduce contamination, but to also help a sector become more competitive. So it was a very positive experience. Also, isotopes can help you in characterizing, for example, seawater intrusion in the case of islands. As I said, our groundwater bodies are in direct lateral and vertical contact with the underlying seawater. And mitigating seawater intrusion requires, so what the actions needed to reduce seawater intrusion in pumping wells requires a clear understanding of the mechanism by which seawater intrusion occurs. Is it primary permeability, so it is slow, let's say the slow flow in the aquifer matrix, or is attributed to secondary permeability, so fast fracture flow, younger seawater. And we're currently concluding a project with the Atomic Energy Agency where we're looking at, let's say, stable isotopes and noble gases and how these can help us identify the flow characteristics by determining the age of the underlying seawater body from which the seawater intrusion occurs in the center of the island. And we're looking at data which shows us that there is a very old groundwater body there. So our definition of seawater intrusion, our mechanisms of seawater intrusion seem to be more related than the ingress of seawater. Actually, the ingress through the rock matrix of an old sail and groundwater body, possibly having, let's say, a very old age, even in the hundreds and thousands of years. So we're concluding this study, which can change and which will change the way we look at intrusion and also the way we try to prevent intrusion. Also, another interesting aspect where we're using stable isotopes is in trying to monitor what's happening in the unsaturated zone, where we have systems, a monitoring system which can sample at different depths in the rock. So we're getting water samples from the rock, and we're looking at if we can detect the seasonal variation in stable isotope composition, so deuterium and oxygen 18, over the year in the unsaturated zone. And therefore, stable isotopes can be used as a tracer to assess the percolation, the quality of the percolation, the infiltration velocities to groundwater in the unsaturated zone. And therefore, this will also help in managing potential contamination events and also to determine what the hydrological conditions which facilitate contamination. And finally, and this is an interesting aspect for countries like us or regions like us which have a significant, let's say, use of desalinated water. Desalinated water has a different isotopic fingerprint with regards to oxygen 18 and deuterium, as you can see from the plot, compared to groundwater. So when one looks at groundwater samples from borehole which have low chlorides but have let's say, have their deuterium oxygen 18 ratio close to seawater, that is an indication of leakages from the municipal water system. So apart from the, let's say, measurement of leakages and everything, you have an indirect method from your groundwater sources which can help you address if there's large-scale leakage from municipal water supplies, be it drinking water, be it sewage, wastewater, due to the different position of the stabilized rock footprint in any obstructed groundwater. And therefore, that also leads to the early identification of leakages, particularly in urban areas or in areas where there's significant water supply infrastructure. So that's from my end 5 aspects of how we used over the years stabilizers.